Today, I'll present our recent work on measurement optimization for excited states in near-term quantum algorithms. Let me start by demonstrating the importance of excited states through an example arising in photochemistry using this diagram. To start, the molecule is in its ground electronic states at the equilibrium geometry. Upon interaction with light, however, the molecule gets excited to one of the higher excited states. And to describe this transition, one must accurately calculate the energy difference between this excited state and the ground state. Moreover, once excited, the molecule is no longer in its stable geometry and undergoes dynamics. And the description of the dynamics often requires energies of not just a single, but multiple electronic excited states, because the molecule often crosses the region where many states are close in energy. The importance of excited state energy calculations and the challenges faced by classical computing algorithms to obtain these energies motivated the development of excited state extensions of the variational quantum eigensolver. And as you may know, the variational quantum eigensolver, or VQE, is the most popular near-term quantum computing algorithm for solving the electronic structure problem. Before discussing the excited state VQE, let me first review the measurement challenge in the familiar ground state VQE and how state-of-the-art techniques improve quantum measurement efficiency. VQE uses the variational principle to solve the electronic structure problem by finding a state that minimizes the Hamiltonian expectation value. So, starting from an initial guess state, say a Hartree-Fock state, prepared on a quantum computer, one applies a unitary operation that obtains a new state, psi theta, with a lower energy. Then the energy of the state is measured on a quantum computer and passed on to a classical optimizer, which suggests a new set of parameters theta to find a new state with an even lower energy. And this process is repeated until the minimum energy is found. One of the bottlenecks of this procedure is the quantum measurement of this expectation value, because as we will show on the next slide, one must prepare and measure the psi theta multiple times on a quantum computer. And if one uses the most naive technique for this quantum measurement, this whole VQE becomes prohibitive, because just for this quantum measurement task, per iteration, it will take hours, even for simple molecules such as water or ammonia. So why is this measurement task so challenging? To measure the Hamiltonian expectation value, one must first represent it on a quantum computer. For the electronic Hamiltonian in the second complex form, this can be done using the Jordan-Wigner transformation. The resulting qubit Hamiltonian is a linear combination of Pauli products, each of which is a tensor product of single qubit Pauli operators. For quantum computers of today can only measure the expectation value of Pauli Z operators. And because the Hamiltonian contains non-Z operators, to measure the Hamiltonian, one can try to find the unitary that rotates Hamiltonian into a polynomial of Z and measure the expectation value of this polynomial of Z in this rotated U psi state. But this scheme is impossible because finding such unitary is equivalent to diagonalizing the Hamiltonian. And this is somewhat more difficult than the original task that we intend to solve using VQE. Instead, one can partition the Hamiltonian into measurable fragments, that is, fragments that are rotated into polynomial functions of Z by U alpha, which are both easy to find and also easy to implement on a quantum computer. Then one can measure the expectation value of each H alpha separately using this expression and sum it up to get the total Hamiltonian expectation value. Note that because U alpha psi is not, in general, an eigenstate of P alpha Z, one has to perform many wave function collapses and gather enough statistics to estimate the Hamiltonian fragment expectation value. Moreover, blindly finding H alpha and the corresponding U alpha is difficult. So in state-of-the-art measurement techniques, one relies on different Lie algebra to simplify this problem, and one can classify the measurement techniques into different categories depending on what Lie algebra is exploited. The first class of methods exploit the commutativity relation between the Pauli products appearing in the Hamiltonian. For concreteness, I use a Hamiltonian containing three Pauli product terms, Z1, Z1, Z2, and X1, X2. The line connecting the two terms show that the two Pauli products commute, and we can see that the commutativity is a bit like friendship, and that a friend of my friend is not necessarily my friend as well. So in this case, Z1, Z2 commutes both with Z1 and X1, X2, but Z1 and X1, X2 don't commute with each other. So how does commutativity help us find fragments of the Hamiltonian that can be easily rotated into Pauli Z operators? It turns out that any set of mutually commutative Pauli products can be simultaneously rotated into Pauli Z operators using a single Clifford unitary, which is easily implementable on a quantum computer. And using this property, one can partition the qubit Hamiltonian into easily measurable H-alpha fragments, and note that a single Pauli product term can appear in multiple fragments so long as the coefficients sum up to that in the Hamiltonian. The second class of measurement techniques are fermionic operator algebra-based methods and works directly with the electronic Hamiltonian in the second quantized form before mapping it to the qubit Hamiltonian. Using one of the decomposition techniques described in this work, one can partition the Hamiltonian into Hartree-Fock solvable terms, that is, terms with eigenstates that are Slater determinants. This decomposition is useful because Hartree-Fock solvable terms are diagonalized into functions of occupation number operators by orbital rotations. Each term then is a measurable fragment because orbital rotations can be easily implemented in a quantum computer with circuit depth that scales linearly with the molecular system size, and the occupation number operator maps to a Pauli Z operator under the Jordan-Wigner transformation. Third class of measurement techniques are Majorana operator-based methods, and as with the other two, the aim is to use the property of the Majorana operators to facilitate finding the measurable fragments. To start, one rewrites the electronic Hamiltonian as a Majorana Hamiltonian using these definitions. The property that can be exploited here is that a Majorana product with consecutive indices map to Pauli Z operator under the Jordan-Wigner transformation, and the task now becomes finding a set of Majorana products in the Hamiltonian that can be simultaneously rotated into this consecutive index form using a single unitary operator. And the unitary operator that can achieve this is the index permuting unitary. So, for example, for this set of Majorana products, an index permuting unitary that permutes PQRS into 2i, 2i plus 1, 2j, 2j plus 1 would rotate all of these Majorana products into the desired consecutive index form. And in this case, these three Majorana products can form a measurable fragment because each index permuting unitary is from a subset of Cliffords, so they're easy to implement on a quantum computer. And these resulting rotated Majorana products either map to a single Z or a product of two Zs. Now we're equipped with multiple different ways to partition the Hamiltonian into measurable fragments, but not all partitioning is equally good. And that is because the number of measurements required to obtain the Hamiltonian expectation value depends on the variances of the fragments, where the variance is defined in the usual way, and M alphas are the fraction of the total number of measurements allocated to measuring H alpha, and epsilon is the desired accuracy that we wish to obtain the Hamiltonian expectation value. And we take this epsilon to be a millihartree. And as we saw before, even within a single class of measurement techniques, there's a lot of freedom of choosing H alpha. And as one example, in the qubit operator-based methods, any choice of X is permissible here because the coefficients would sum up to that in the Hamiltonian, regardless of our choice of X. There are two general tactics to find the H alpha partitioning, and one is a more randomized approach, and the other is a more optimized approach. The randomized technique, one starts by choosing a unitary U alpha randomly from a given set of unitaries. For example, the set of unitaries would be Clifford unitaries in the case of qubit operator algebra-based methods, and index permutation unitary in case of Majorana operator-based methods. Then one applies this unitary to a total Hamiltonian and measures every term that gets turned into a Pauli-Z operator. While this expression here is specific to the qubit Hamiltonian, the same idea applies to the Majorana Hamiltonian. So the series of randomly chosen U alphas would define the Hamiltonian fragments H alpha. This randomized approach works well for measuring a large number of different observables, but for measuring the expectation value of a specific operator, like in the case of VQE, the required number of measurements is typically very large with this randomized approach. To mitigate this issue, an extension was proposed called the de-randomization extension of classical shadows. And this de-randomization technique uses the knowledge of Pauli products appearing in the Hamiltonian to inform the choice of U alpha. The methods that lead to the lowest number of measurements in ground state VQE, however, are fully optimized techniques. And these fully target-focused techniques go beyond just using the Hamiltonian information and use both the Hamiltonian and wave function information to minimize the number of required measurements. But of course, because we don't have access to a quantum wave function, we don't have the exact variances. But in chemistry, we often have a way of obtaining classically efficient proxy, for example, by performing configuration, interaction, singles, and doubles calculation. And one can use this approximated variances to minimize M. In the previous video, I discussed in detail some of the optimized techniques developed in our group in the context of ground state VQE and analyzed their performances. I'll put a link on the top right corner for this video. So while optimized measurement techniques outperform randomized techniques for ground state VQE, in the case of excited state VQE algorithms, there are more than just a single observable to measure. So this makes it unclear whether the optimized techniques, which took advantage of the fact that we can target a single observable, would still perform well. So in this work, we assess the various measurement techniques in two popular excited state VQE algorithms, multi-state contraction and quantum subspace expansion. In the next two slides, I'll briefly discuss them and discuss what observables one needs to measure in these two excited state VQEs. MCVQE, or multi-state contraction VQE, modifies the ground state VQE algorithm and finds not just one, but n lowest energy eigenvalues. One starts from a set of n orthonormal classical efficient guess states, for example, configuration, interaction, single states, and performs VQE to minimize the state average energy of these n states. The key idea here is to apply the same parameterized unitary to all n guess states, because if different unitaries were to be applied to each guess state, the orthonormality would be broken and the states could all collapse to the ground state. And instead, by using the same unitary, the orthonormality is preserved, and this VQE procedure converges to the n lowest eigenstates of the Hamiltonian. The cost, however, of the quantum measurement step is the sum of measuring the expectation value of all n parameterized states, and therefore is higher than the ground state VQE. Quantum subspace expansion, QSE, is another popular excited state VQE algorithm, and the main idea here is to perform a truncated configuration interaction, for example, CIS, using the final converged state from ground state VQE as the reference. And to solve this generalized eigenvalue problem that arises in CIS, one must measure the relevant matrix elements on a quantum computer using this converged psi theta star states. So unlike in MCVQE, where one had to measure expectation value of the electronic Hamiltonian with many different states, in quantum subspace expansion, one measures the expectation value of many different operators. So these OJ, and OJOK operators in the same state, psi theta star. These operators can have very different energy scales because these excitation operators can be from the lowest occupied to the highest unoccupied orbital. And therefore, it is expected that the optimized techniques would perform less well in the context of quantum subspace expansion. The expression for the measurement cost of quantum subspace expansion is given here, and it turns out to be equal to the cost of measuring the most expensive operator out of all these operators to be measured. Here, I finally compare the performance of various measurement techniques in multi-state contraction and quantum subspace expansion by showing the number of required measurements averaged over 8 molecules listed here. Because it would be too costly to estimate the measurement costs of every MCVQE iteration, I've instead estimated the cost of the final MCVQE step and multiplied this by 50, assuming that a typical MCVQE calculation would require about 50 steps to converge. Moreover, we also assume that we're interested in finding the energy of 10 lowest lying states. The plot here shows that for MCVQE, optimized techniques outperform randomized techniques because the lowest 10 eigenstates are still similar enough in character for the optimization procedure to be effective. This is further supported by how the best randomized technique is the de-randomized extension of the classical shadow. But on the other hand, in QSE, because we have to measure observables of vastly different energy scale, optimized techniques are no longer very effective, and randomized techniques work best. In particular, the Majorana classical shadow techniques perform best for QSE. However, we see that even with the best measurement technique, QSE is too costly, requiring about 15 billion measurements, or about 10 days on a quantum computer. On the other hand, 50 iterations of MCVQE with the best measurement technique, that is, fluid fermionic fragments method, is still feasible and takes only about a couple of hours. To conclude, we have studied the performance of measurement optimization techniques in excited state VQE and found that the combination of fluid fermionic fragments and multi-state contraction has the lowest quantum measurement costs, making them the most promising excited state VQE technique regarding measurements, with the measurement cost being approximately 4 minutes per iteration on today's quantum. Here is a citation to our related work, and thank the Swiss National Science Foundation for funding. Thank you very much for your attention.